Hello and welcome to EasyMotion Studio video tutorials. This tutorial will cover the basics of drive setup. Although at the first glance might seem that there is a lot of information present, the drive setup window is actually split to different parts. The core parts of the setup that have to be validated in almost any application are the control mode, the commutation method along with start mode, the drive operation parameters, the controllers, and the protections. The other parts are there to give more freedom to the user in configuring the application and will not go into detail with them at this time. The control mode is self-explanatory and allows you to select the control parameter, torque, speed, or position. It must be mentioned that the control loops are closed on top of each other. So, for example, when you select position control, you will be able to control the torque as well. You might have noticed already that the default configuration for position control involves only the position and current or torque controller. This is the case for the majority of our applications where the goal is to have high bandwidth on position loop in order to be able to perform short and fast positionings with tight following errors. The speed controller, which can be enabled if needed, is acting as a filter, a delay in the control chain, and is therefore recommended only for applications where switching on the fly between position and speed control is required, but the position performance is not critical. Even though that the speed controller is turned off, you can still have a kind of speed control by using very long position profiles with periodic position reset if needed. Finally, for cases where both critical position performance and true speed control is needed, a special setup procedure can be made. But for the purpose of this tutorial, we'll stick with the defaults, position over current structure. The commutation methods allows us to choose sinusoidal or trapezoidal. The trapezoidal mode is basically a legacy mode where the motor is controlled as BLDC, brushless DC, and the currents have rectangular shape. The whole commutation method is simple and based on the presence of the digital Hall sensors. Only two phases of the motor are energized at any given moment, and therefore both the noise and the torque ripple might not be on minimum values. The sinusoidal mode is the default one and more complex mode, where the motor is controlled as BLAC, brushless AC, using field-oriented vector control algorithms with the help of the encoder. The currents are now sinusoidal and all three phases are supplied in the same time. This mode offers smoother operation than the trapezoidal mode, especially at low speeds. The notion of start mode is given by the relative aspect of the incremental encoder used on this template. The digital Hall sensors, which are carefully placed and calibrated by the motor manufacturer, work as absolute sensors over one electrical rotation. This is the reason why when trapezoidal mode is selected, there is absolutely no start mode option at all. Sinusoidal mode means vector control with optimum commutation, and this means that the drive needs to know at every moment the precise position of the rotor. Since the incremental encoder is a relative sensor, meaning it can only tell how much did the motor move from the starting point, before the drive can properly control the motor, it will need to somehow determine the initial rotor position. This is called the start mode. Our drive currently supports 4 starting modes. The move till aligned with phase A procedure, also known as pole lock procedure, consists of aligning the motor with a certain current and for a certain time to a known position in open loop. In other words, if I can't know the rotor position at power on, then I have to move it to a position which I'm certain to know. In our case, this means to supply the motor in such a way that it will align itself with phase A before I start using the encoder information. Because the motor can be in any positions, this alignment move can be shorter or longer. So in other words, it is not controlled in amplitude. The BLDC with Hall sensors is doing the same thing but in a different manner. And that is using the Hall sensors to determine the rotor position before the encoder is initialized. The advantage of this method over the previous one is that the motor is controlled in trapezoidal mode for the first 60 electrical degrees and then switch to sinusoidal mode. In this way, the uncontrolled movement at the start is eliminated. The PMSM with Hall sensors work in a very similar manner with the BLDC with Hall sensors, and it offers an alternative. The motor starts directly in sinusoidal mode, and after the first 60 electrical degrees, only a compensation is done. For the vast majority of the applications, the user can't tell the difference between the last two modes, but for those really special applications, the PMSM mode with Hall sensors offer an even smoother start, as there's no trapezoidal mode at all. It is important to note that both of these methods require the presence of digital Hall sensors. The last one, motionless start, is also aimed at avoiding the uncontrolled motion of move till aligned with phase A, even when there are no digital Hall sensors present. This is the most complex starting method, as in this case the drive tries to determine the initial position of the motor by adjusting the electrical field in the stator without virtually any movement at all. And such it requires the additional tuning of an electrical angle controller. The main drive operating parameters are power supply voltage and current limit. The power supply voltage, which can be measured using the embedded test, is very important because it acts as a scaling factor in different places. This is the reason why we should always use the determined value rather than the old one, especially if they are very different. Besides this, it is also continuously monitored and used as under voltage protection or over voltage protection, and if needed, it also acts as a trigger for the external brake resistor inverter leg. The current limit represents the value that the drive will always limit as reference to the motor. This means that in any closed loop mode of operation, no matter the circumstances, the current reference will not exceed the user-imposed limit. In our case, since the motor has a peak current of 2.55 amps, we will set the current limit to something slightly lower, like 2 amps. Next, we'll take a look at the most difficult part of the whole drive setup process, the controller's tuning. If you remember, the control loops are closed one on top of the other, so it becomes mandatory to start the tuning process with the inner loop. In our case, where we'll be using a position current structure, this means that we'll have to start with the current controller by pressing the tune and test button. The current controller is a digital PI controller, and the tuning consists of finding a pair of parameters for the proportional part and the integral part that will make the system behave in the desired way. To check the functionality, a current step reference test is used, and in this window, the test parameters tab, we get to configure it. The step value follows the behavior like it was during the motor tests. The default value is half of the nominal current, but we'll now change that to be closer to the nominal value. since depending on the controller's parameter, the actual current through the motor might deviate from the imposed reference, the overcurrent protection will be active during the test and we can adjust it if needed. As the proposed value, which is the peak current of the motor, is leaving us enough room for testing, will not change it. When the test parameters are set, we have to move to the Test tab. Here, we can adjust the Kp and Ki, that is the proportional gain and the integral gain of the controller, in two ways. The direct way, that is manually changing them, either by typing in the desired value or by using the sliders, and the indirect way, by using the Tune button, that based on the passband parameters and motor data, along with the voltage level, will compute a set of Kp and Ki values. The minimal way of explaining the passband is that the higher the value, the faster and sharper will be the controller response. In other words, the controller will be able to follow higher frequencies in the reference, therefore we can say that it has a high bandwidth or passband. The recommended way for tuning, and this applies to the other controller as well, is to start by setting a passband, then press the Tune button to get a set of parameters, then run the live test that is applied to the motor, and based on the results you can decide if more iterations are needed or if it is good enough. Here's how to interpret the graph. The yellow line, which has the vertical axis on the left side, is the current reference. You can do zoom in by holding the left mouse button and dragging a square to see, for example, the step reference 0.9 amps, and to zoom out you simply double click the screen. The magenta line is the actual motor current. This is the response we should be investigating. When tuning the current controller, we must look for a motor current that rises as fast as possible, overshoots as low as possible, and remains stable all the time. We can see that the current reaches the reference in little less than 2 milliseconds with no overshoot. The blue line, with the vertical axis on the right, notice the small YR before its name, is the voltage reference. The graph can be considered good in many circumstances, but considering the way a PI controller responds to a step input and the fact that the voltage doesn't go into saturation, there is still room for improvement in our case. We can next increase the passband, use the Tune button again, and repeat the test. We obtained a better answer, but still no signs that we are on the limit. There is still no visible overshoot or any instabilities. So we can repeat the step, increase the passband, press the Tune button, and start the test. While at some point the parameter for the passband will no longer be able to increase, you can always change the Kp and Ki parameters by hand. Since this repetitive process is called fine-tuning, it won't be detailed at this time, but I'll illustrate two types of wrong tuning parameters. The one that will give some self-sustained oscillations, which happens when the gains are too high. You can see the oscillations in the motor current and also on the voltage. or when the parameters are simply too low, and you will get a delayed or sluggish response. Notice please that the test is considered succeeded in all the cases. Basically, the software will give this verdict on any instance that hasn't tripped the error. So you can't actually rely on the software to tell us when the tuning is good or not. You will have to decide that yourself.
After having found the parameters for the current controller that provide the performance we are looking for, we can move on the next outer controller, in our case the position controller. The tuning is done in a similar fashion. We start by pressing the Tune and Test button, we configure the test that will be performed, and then run the test itself to check the results. This time, the test involves rotating the motor to allow us to see the positioning performance. The position profile used is defined here, and it can be configured as multiple cycle movement, which permits us to see the instant effect of the controller parameters adjustment. The actual positioning will start from 0 and will be 2 rotations. The time needed to do those 2 rotations is defined here, as well as the time needed to get back to the initial position. We also have the possibility to add some wait time between the movements, and in this case they are 1 second. As you can see, the positioning profile is fully customizable to match as close as possible the application requirements. Just like any other live test, we have to check the current limits and the protection levels. The starting current parameter is related to the start mode, move till aligned with phase A, and since the position controller tuning must be done with the motor connected to the load, this value should be high enough to ensure correct initial positioning. That's why we recommend setting this value to 100% to ensure using the whole nominal current of the motor. On the test tab, we have the same tune button, but to make sure we get the best results, we must run another test that will allow the drive to estimate the total system inertia. The total inertia test is based on the simplified formula that says torque equals the moment of inertia multiplied with the angular acceleration, and therefore the motor will be applied a torque step, and the evolution of the speed up to the maximum allowed value will be recorded internally to determine the acceleration. Knowing the torque and the acceleration, the inertia is then estimated. Now that we have an idea about the total inertia of the system, we can press the Tune button to get an initial set of parameters, and then we can start the actual test. Please notice the initial positioning move till aligned with phase A is performed, and then the actual positioning used for tuning is started. While the motor is moving, we can see on the oscilloscope view the graphs for position and current. With yellow, we have the positioning target reference, which is the profile we have selected, and with purple color, we have the actual load position. With these tuning parameters, the load position follows very closely the reference, and that's why both traces are actually one on top of the other. In the same time, we can see the current reference, shown in turquoise, and the actual motor current, shown in green. Notice please the current offset, which actually means that on the oscilloscope view, the zero level for the current is on this point, and is not the same with the positioning plot. This is done to make the screen easier to read. As the motor doesn't have any load on it, the needed current is, as expected, close to zero, and if I apply some load to it by hand, you will immediately see the position controller response. It has increased the torque command to ensure the motor still follows the imposed position. The same tuning reasoning like in case of the current controller applies for the PID position controller as well. Too low parameters result in sluggish performance, while too high parameters will make the system unstable, basically overreacting on the smallest error. The test is finished when we get the desired performance, at which moment we stop the movement and press the OK button. The last step implies checking and changing, if needed, the protection values. The overcurrent protection is aimed at safeguarding the weakest component of the system, which in this case is the motor. It is doing that by monitoring the current and cutting power to the motor by disabling the drive power stage if the current exceeds the selected value for a certain amount of time. Please note that even if the current limit is set to a lower value than the overcurrent threshold, because that only limits the current reference, there can be situations where the current flowing through the system exceeds that reference. And as such, the overcurrent protection must be properly configured in any situation. The next protection is called control error, and it's actually a similar mechanism like overcurrent, only that it acts on position. If the difference between the imposed position and the actual position read from the motor is constantly higher than the defined value, for at least a certain amount of time, the drive will consider this situation as an error and will react to this condition by disabling the motor. The last protection to be configured is called I2T. This protection is meant to cover the area between the motor nominal current, 1 amp, and the overcurrent limit, 2.55 amps. As any type of motor allows for short duration overloads, and we have already considered that by actually allowing 2 amps through the motor, the I2T protection will set a limit on this allowed overload. The idea behind it is that when the current through the motor exceeds the nominal value, the motor will start to generate heat through current losses faster than it can dissipate it, and therefore it will start to overheat. Based on this fact, the I2T parameters are used to define the overload capacity of the motor, and that will ensure protection for the whole area above motor nominal current. To better understand the functionality of I2T, we can refer to the help file where we can see the pair for overcurrent and time are actually defining the I2T hyperbola of the motor. It follows that for a different current, the corresponding overload time will also change. Higher current will result in smaller time, which makes sense because the motor will actually overheat faster, while smaller currents that will result in higher time can still overheat the motor. So, by properly selecting the I2T curve for the motor, which should be given by the motor manufacturer, we are protecting the motor not only for currents bigger than 2 amps, but for anything that can overheat the motor. Finally, when this is done, we have a good setup for the motor and drive, and the last step before being able to program the drive as needed is to download the setup table on the drive non-volatile memory. We can do that by pressing either the download to drive motor button from here or this button from here. They have the exact same functionality. Congratulations! At this point, we can move on to programming the drive.